So example 6 is piecewise fun, as it says, and we're going to be using the IVT. So what we're doing on example 6 is determining if the IVT will apply on the following intervals, and then explain why or why not. So we're not going to use the IVT. We're just going to see if the IVT applies. So before we do that, would anyone care to summarize what the IVT is? I think we tried that already. It stands for the intermediate value theorem. Excellent. That's a good start. I'll take that. Which is talking about a y value. Good. So it's the intermediate y value theorem. So you can call it the YVT, right? What's the if part? I, y, sine, height, YVT? If what? What's it? If some function is continuous on a closed interval. Good. That's it. Then yeah, something like that.
Goes through everything. I guess, like, in the between. So the y value it starts at and the y value ends at every y value between.
There you go. That's a good way to say it. Yeah, it's kind of hard to phrase the y value of the starting point and the y value of the end point. It'll touch every y value in between, which is a good way to paraphrase it. And also there is an x value between x equals a and b that'll generate each one of those y values. So really, you can find the x value. And we talked about that yesterday up here. If we know the temperature at one time in a spot and the temperature at another time in a spot, we know there had to be some time during that time interval, which is like our x values, where the temperature was every temperature in between our two readings. We don't know when, but we know it had to exist. So this is an existence theorem. So let's see if the IVT applies on these intervals, which means we're just going to be looking to see if the function is continuous on these closed intervals. So the first one's from -4 to -2. -4 to -2. Which piece are we looking at from -4 to -2? Exclusively the top piece, right? Because it's less than or equal to -2. Will the IVT apply then? Yes, because a line, which is what this piece is continuous everywhere, and so it will be continuous on the open interval, and it will be continuous at the right endpoint, which was really going to be the only problem. Continuous at the right endpoint. We know that it is because less than or equal to means the left-sided limit is equal to the function value by definition. So this one is yes. We'll just put a big Y for yes. All right, how about from -3 to 0? -3 to 0 now spans two different pieces, doesn't it? It starts on this one, but it ends on this one. So let's look at the endpoints first, okay? Is it going to be continuous at the left endpoint, -3? Yes, because it's part of a line. Is it going to be continuous at the right endpoint, 0? Yes, because it's part of the parabola. So now we only have to check if it's continuous on the open interval. Well, there's only one place on the open interval from -3 to 0 where it might be not continuous, and that's where? -2, the baton exchange point. So let's see what the left-sided limit is and the function value. We plug in a -2 and we get 5. So that's 2 to the 3. The limit from the right of -2 is 5. Does 5 equal 5? Yes. Or 5 equals 5 equals 5. So they are exchanging the baton successfully there at -2. Bless you. And therefore, is it continuous then on the closed interval? Yes, the IVT applies. Sweet. All right, from -1 to 1. We're spanning one interval or two? Really two. -1 starts on this interval, but notice it's strictly less than 1. So we do need to check at 1. Now, I think it's going to be continuous at the left endpoint, -1, because it's on the midpoint or the interval of the parabola. The only thing we need to do is check the right endpoint. Let's go ahead and write down that notation. To be continuous at a right endpoint, we saw yesterday, the limit as we approach that right endpoint, which is 1, from the only side we can approach a right endpoint, which is from the left, we need to compare that to the function value at 1. If they are the same, then we know that the graph is coming in and stopping where the function value is. So what is the limit from the left of -1? Plug it in and get 2. And what is f of 1? Plug it in. 3. Does 2 equal 3? No. So is it continuous on this interval? No. So let's go ahead and say no for the first time. No, complete sentence, not it, but f of x is not continuous. Is not continuous. Where, in France? Good. At x equals 1 since, and 3 is not equal to 2. Good. It's not continuous at the right endpoint. We have the justification up there with the proper notation. And notice we're doing this analytically. We're not even looking at the graph, which is kind of how you want to be able to do it.
So if it ever asks you to determine the IVT, would still be in the three-step definition?
Yes, essentially, because remember, to be continuous on a closed interval, it has to be continuous on the open interval and at both endpoints. So we're only really doing the two-step definition of continuity here, because at the endpoint, remember we loosened up the restriction. We only looked at the left-sided limit and the function value. We didn't have to compare it to the right-sided limit because we were testing the right endpoint.
On the free response, would you have put no, the IVT does not apply?
No, but you could. It actually asks you to determine if the IVT applies, so when you say no, they'll assume you're answering that specific question. But great question. Doesn't hurt to put it in there. Okay, how about from 1 to 4.5? Is that spanning one interval? 2, because 1 starts on the middle interval and ends just to the right of 4 there. All right, okay, so what do you think? Is it continuous at the left endpoint 1? Yes, because we know now that it's greater than or equal to. So greater than or equal to means that the limit from the right of 1 is defined to be the same as f of 1. So we don't have to check the left side limit. Or I'm sorry, the left endpoint. What about 4.5? Is it going to be continuous at 4.5? Well, 4.5 is going to be on this graph. And we're between 4, where the graph starts, and, oh, careful, there's a built-in discontinuity where? At 5. But we're only going to 4.5. So in between the exchange and the vertical asymptote, the graph should be continuous, right? So it should be continuous at the right endpoint. So that's good. But we do need to check the open interval. We need to see what's going on where. What's the only place then where it might not be? 4. So you could do it informally in your head first and then write your formal argument. What's the limit from the left of 4? Plug it in. 6, good. And the limit from the right of 4 and the function value of 4, plug it in. 6. Does 6 equals 6 equals 6? Yes. So is it continuous at 4? Yes. So now is it continuous on the open interval from 1 to 4.5? Yes. And we already tested the endpoint, so this would be a yes. Okay? That time we did do the three-step definition because we were testing the point in between there. All right, how about from 2 to 7? Very good. That one's easy. 2 starts here. We already know that it's going to be continuous at 4, but we have a vertical asymptote right at 5, and there's no getting around that, okay? So that's not going to work. So you can say no, f of x is not continuous at x or on the interval. Oh, I said at x equals 1. Yeah, at x equals 1. I didn't really answer the question earlier. You could say at x equals 5. I kind of got confused over here with what the question was asking. I got my tunnel vision. F is not continuous. The question was on the interval. On, sorry, let me come back. -1 to 1. Since, so now we're answering a different question. Yeah, since f is not continuous, my bad, at x equals 1. No. Because it's a different question. Yes. It's not continuous on the interval. On the interval from 2 to 7, since f is not continuous at x equals 5. If you wanted to say there's a vertical asymptote at x equals 5, you could do that too. But this is kind of bland. It's vague, but it answers the question specifically. So let's learn from my mistake. Always make sure that you're answering the very specific question that was being asked, because I didn't. And I know with iPad it's easy to kind of get tunnel vision, especially when you're zoomed in like that. All right, so kind of a nice little problem. I could ask a question like that tomorrow on the free response as well. That was a pretty nice one. Yes, since f of x is continuous on the close on negative 3 to 0. Yeah. Let's go ahead and write that. Yes, f is continuous on the interval from negative 3 to 0. Well, there's really no sense. You're just answering it. Since f is continuous on the closed interval from negative 3 to 0. Yes. Oh, yes, the IVT applies since. There you go. I know. I'm sorry. It was a crazy lunch. I had to leave the room. I'm not used to that. Had to find my way back. There is. Yes, the IVT applies, comma, since f is continuous on the closed interval. Got it. We're not trying to prove continuity. That's just what we're doing to determine if the IVT works or not. No. She just asked what we could put, so you could just put yes. All right. So let's go ahead and use the IVT now instead of just seeing if it works. If it does apply, then how are we going to use it? You don't like particle motion. Well, here's a taste of particle motion. The velocity of a particle, moving horizontally, left and right and left and right and right and left and right and left on the x-axis is given by the continuous function v of t. Selected values are given below. Let's see what selected values have been chosen for us. Time is 0258. Nice. Those are good times. Good times. 3.52 and 1. So the velocity units could be like feet per second, miles per hour. Yes. Oh, that's why they're spaced off there. Man, great one, Eugene. You're a hero. I in the next 2 days, when I have a little time, I'm going to come back and just re-PDF all these and repost them. I don't say that every day. I say I need to, but I didn't say I'm going to. Peter, you need to listen carefully. I said I need to do it, but I didn't say I was going to do it.
Every Friday after I ask, don't redo the board. Monday I come in and he's like, almost didn't, and I remember that I told you I would.
Right. So now I have to, Peter, because I said I would. Peter, you see, you're not listening again. Okay, thank you for listening, Peter. All right. So here we go. It says explain why. My bad. I got you all riled up. Explain why there has to be a time on the interval from 2 to 5 where the particle changes direction. Oh. Okay, so let's think of what velocity is. Velocity is speed with direction. It's a vector quantity. So if we're moving on a horizontal axis, a negative velocity means your position is decreasing. So you're moving to the what? Left. And positive velocity means that your position is increasing, so you're moving to the right. And it did say it was a continuous function, right? So when will it change directions? When the sign of the velocity changes from negative to positive or positive to negative, right? It's going from left to right or right to left. Because it's a continuous function, it's a negative velocity at 2 and a positive velocity at 5. Is there any way for this particle to go from negative to positive without changing signs through a continuum? No. Because it could be that it's just negative here and it's negative the rest of the time and just all of a sudden, boom, becomes positive at 5. And that would not be on the open interval, but that's not how things work. So there has to be some time in between 2 and 5 where it actually crosses the t-axis, right? And when it does, it's going to pass through 0. So basically, if we could prove that it passes through 0, we'll have it. So here's what we're going to do by the IVT. Since V of t is continuous, let's try that again, continuous on the closed interval from 2 to 5, and since V of 2 is less than 0, and V of 5 is greater than 0, comma, by the IVT, And we'll go ahead and invoke the name of the IVT. That's a very important one. By the IVT, comma, and now you just use their wording. There must be a time where the particle changes direction. There must be a time on the interval. I'm going to use interval notation 2 to 5. We can actually free up the equal signs if we want, because we know it's not going to happen at the end point. But if you want, you can still put the closed interval. We know it has to be somewhere between 2 and 5 exclusively, where the particle changes directions. So this is going to be pretty similar with the other two VTs that we end up talking about. You're going to give your evidence, and then you're going to basically restate what they're asking you to do, which is what I wrote in purple. So the important parts of the IVT are basically to show what the Y value of one side is and what the Y value of the other side is, and then show that the Y value that you're looking for is in between there. Now this one's a little bit different because it didn't specifically ask us prove that the velocity had to have been 1 at some point in between there, which it does, right? There had to be a time between 2 and 5 where the particle's velocity was 1, because 1 falls between these two values. This one is a little bit more broad and vague, show that it changes direction. So what we did there is we said there's no way through a continuum to go from a negative to a positive without changing directions or changing signs through a continuum. Now, do we know exactly when it changed directions? No. We just know somewhere between 2 and 5. Okay. Let's look at some other examples. Then I want to work example 10, which is the last one. You'll have one like this on the worksheet. It says, show that there's a positive real solution to this equation. Show that there's a positive real solution. Now, the first way to show that there's a positive real solution is to actually find it, right? And put it in your hand and pass it around and say, here it is. Here's the positive real solution. And most people are going to be like, seeing's believing. There it is. Hey, you proved it. You proved it to me. I see it. Does anyone know offhand what value of x makes that true? Me neither. Okay? But maybe there is a value. Is it easy to solve for algebraically? I don't think so. But we could still prove that there's a positive real solution without actually finding it. And here's how you would do that. Just like if you were going to be graphing it on your calculator, get everything on one side and set it equal to 0. And the reason you want to do that is, as we've already seen, it's easy to show that a y value has to equal 0. Because you're not looking at numerical values, you're just looking at signs, positive and negative. And if it passes through that through a continuum, you know that it's got to be passing through 0. So what we've done is we've changed the equation, but we haven't changed the solution. So now if you want to think of this as being f of x, here's what we're trying to prove. We've kind of restated the problem. We want to show now that that function has a 0 in positive real world land. And it's our job then to figure out between which x values it might fall. So here's what our goal is. I'm going to do a little trial and error. I want to pick an x value that's positive, or non-negative, I should say, so that when I plug in here, I get a positive number, and then another one so that when I plug it in, I get a negative number. If I can find two numbers so that when I plug them in, one's positive, one's negative, because it's a fifth-degree polynomial, which are continuous where? Everywhere, then I know that there's no way for it to go from negative to positive or positive to negative through a continuum without passing through 0. And therefore, I will know an interval on which the solution must live. So that interval could be as big or as small as I'd like, as long as it's a positive solution. So, what do you want to try? 2 and 1. Dang. Let's see what you get when you plug in a 1. 1 minus 1 is 0. 0 minus 2 is negative 2. So that's a negative number. Let's try that. I'm going to write that down. So f of 1 is equal to negative 2, which is less than 0. And you said 2? As long as it's positive, it's okay. That's going to be 32 minus 2 is 30. 30 minus 2 is 28. Is that good?
There's got to be another way.
Well, I like that. That's not bad. 1.5. Do you want to plug 1.5 in and raise to the fifth power? Yeah, me neither. So this is good enough. So here's what we're going to say. Now here's the inequality, and this is kind of a real important part to it. we actually have a target y value now of 0, not just windows that change signs. So here's what we're going to do. It turns out that f of 1 is smaller. So since f of 1 is less than or equal to 0, which is less than or equal to f of 2. Or you can use the actual number. Since negative 2 is less than or equal to 0, it's less than or equal to 28. And since x squared, I didn't name it. Well, I did. I called it f of x. Let's do that. And since f of x is continuous, where? You could say for all x. Don't say everywhere, but you say for all x. I would recommend keeping it a little bit closer to home. You're not wrong to say for all x, but when you say it's continuous from 1 to 2, it does two things. It makes the interval a lot smaller, so in case you're wrong about it being continuous for all x, you're not going to misspeak. And it also speaks directly to the x values you were working with, which shows a little bit more understanding of the theorem. Both are perfectly fine, though. Since f is continuous on the enclosed interval from 1 to 2, and since 0 is between f of 1 and f of 2, comma, by the IVT, there must be what? There must be a solution, and we could just reference the solution. That's their wording. On the interval, how about this? On the interval, x equals 1 and 2. And we can use parentheses here instead of brackets, correct? Because we know at 1, it's negative, and at 2, it's positive. So somewhere on this graph between 1 and 2, it crosses the x-axis. Do we know where between 1 and 2? No. Can we find it? If we had a calculator, it'd be real easy. All you'd have to do is graph what we did in y1 and graph 0 and y2 and find where it intersects. Are you interested in finding it? I'm not either. I'm good enough to know that it's there. Okay? It's there. Yes, because we set it equal to 0, we now have a target y value. And it's nice when you can have a target y value. Because then what you're doing is you're finding y values at endpoints of intervals, and all you have to do is show that the target y value lands in between those. Say the function's continuous, and then we know that there has to be at least one value between those x values that generates that y value.
Sorry, you said the two values have to be outside of one higher and one lower than the target value?
Yes, the y values do. You're choosing x. In this case, we chose x values. Yes, they have to give y values that are on either side of your target value. If I would have chosen two values that were both positive, that wouldn't have worked.
So, but you just try new ones.
Yeah. I mean, I could have chose 1 and 100, right? And 100 would have given me a positive number. And I said somewhere between x equals 1 and 100, there's a solution. Great. You know, so the smaller the interval, the better. Maybe 1.5 would have worked, but quite honestly, I was too lazy to plug in 1.5. Y'all offered it up, and I said no, too lazy. But that would have narrowed the window down. So that's one way to use it. 9 is pretty much the same way, but notice you're given the interval now. So you don't always have to like pick x values and plug them in. In this case, you're just going to find f of 0 and f of 2 and see if it works. Now let me do example 10 real quickly, because this is what was on the AP exam several years ago, and it was the lowest scoring question, I think, in the AP exam's history. This was 2007. It says the function f and g are continuous for all real numbers. The table gives values for the selected values of x. If h is given to be f of g of x minus 6, explain why there has to be an r value between 1 and 3 such that h of r is negative 5. So one of the things about the IVT is recognizing you have to use the IVT. The r thing threw people off. But if you look over here, it says h of r, which means r is what, an x or a y value? It's an x value. So they're saying basically show that there has to be an x value between x equals 1 and 3 such that the y value there is negative 5. H of r, it's a y value. So if you're trying to prove that a y value exists, what theorem do you use? The YVT, which is the IVT. So here's all you have to do. You just have to say h of x is continuous for all x from 1 to 3. Now, how do we know that? It tells us f and g are, right, for all x. What do we know about compositions of two continuous functions? It's also continuous. So, number one, you're just going to say h is continuous on the interval from 1 to 3. Check. And then you're going to figure out what is h of 1 And then you're going to figure out what is h of 3. Now, where are you going to get those? Let's get those from the table very quickly. H of 1 is f of g of 1 minus 6. So what's g of 1? You get it from the table, it's 2. So what's f of 2? 9. And then 9 minus 6 is 3. And then h of 3, what's g of 3? 4. What's f of 4? 1. So what's 1 minus 6? Negative 5. We want to show that it equals what? Is that right? Did I do that right? Did I type it up right? 1 to 3, h of 3, g of 3, g of 3. Did we do it? 4. Negative 1. Oh, okay. It's missing a negative. I was going to say that's not going to work. Okay, thank you, thank you. So then f of 4 is negative 1. So I get negative 1 minus 6 is, or negative 1 minus 5 is, wait, negative 1 minus 6 is negative 7. Yeah, my bad. There's a negative there. Dang those negatives. Okay, so do we have it? Yes. And then here's what you'd say. Since negative 7 is less than, you could say less than or equal to negative 5 is less than or equal to 3, comma, by the IVT, and then all you have to do is state their words. There must be a value such that. And that's it. That's right. Yeah, let's make the homework due tomorrow. But I'll make the test easy because the homework's due tomorrow. Sound good? You're welcome. IVT is the YVT to prove a Y value exists.